So, let us just conclude on this solar energy harvesting part. Okay. Let me give you some numbers which will help you to design systems. Do you recall that we were trying to play with this yesterday, and I was trying to tell you that this is a small solar panel, and I also showed you the kind of lux that you will get indoor as well as the lux that you will get outdoor and all that. From our understanding of this particular calculation that I showed you with respect to the area of the solar panel, we said that if you have 1 centimeter square panel you should get 10 milliwatt. So, let me, it is cluttered here. So, let me just shift back. 1 centimeter square centimeter should give you 10 milliwatt. Okay. This is actually 6 centimeter square. This is actually 6 centimeter square, the panel on in the hand, panel in the hand. Okay, I have just put it here. This should give you 60 milliwatt, right, of power. So, on paper it appears that this should give you 60 milliwatts of power, but I just looked at the manufacturer's specification. This is available in DigiKey. You can buy it from DigiKey, DIGIKEY, and it has a part number. I can give you 8691006 ND. Okay, this is from Panasonic. This is from Panasonic solar panel, and this base substrate is actually glass. The manufacturer's claim is that this is only a 20.7 microwatt panel. This is a 20.7 microwatt panel. Clearly it is not matching to what we discussed, right, about all this 1 centimeter square giving you 10 milliwatt and all that. So, what is the big summary? Big summary is you have to take the specification of the manufacturer seriously, and you have to do a VI characterization of the panel. This is the truth. You have to do a VI characterization. Once you characterize the VI, use that VI which you have made your own measurement in the lab and use it accordingly for your application. Okay. One simple thing that you can actually now go back, because we discussed about LT spice, simulation with on LT spice and so on. You can actually go back and use this board which actually has the LTC 3105 here, and connect it to this input here and see actually under practical conditions what is the voltage developed across the output, because this has been programmed for giving you 3.3, and all of that should go into this capacitor, right. This is a super capacitor here. Remember that condition monitoring of ball bearings example that we started with. Essentially you are trying to harvest from the magnetic field, all that. So, essentially it is the same board. So, we are trying to so the idea is that you should be able to harvest and actually find out how long it takes to charge this. Go back perhaps into your simulation model with the LT spice and in LT spice, and design back and put back values for the LTC 3105 circuit and resimulate it. You can either do from implementation come back to simulation, or ideally you should go from simulation to the actual implementation, because when you really want to prototype, the first step is to even before you buy any component, because these are little bit on the expensive side, you may actually want to try out from all the available free software tools. Okay. So, I can also tell you that this is a bigger panel which we got from another vendor, and perhaps the right solution would be to interface this panel with this LTC3105. This is a bigger panel. Okay. This is 400 milliwatt panel. This is a 400, no, I think it is a 600 milliwatt panel. We said it is a 600 milliwatt panel. So, this is really a 600 milliwatt panel, and perhaps this should be okay for your application. But you see now the size of this panel is uncomparable to the size of the electronic, and what application it will have, you have to really imagine before you try to deploy it for indoor applications. Okay, very good. So, this is about the solar discussion, solar panel LTC3105, the way you have to configure LTC3105, LTC3105, its feature of using MPPC, right, where you are setting this maximum power point control feature. If you have, let us say, 2 panels which are stacked in series, you may actually want to set it to 0.7 volts and ensure that the panel never collapses, yet you are able to extract energy, power from the panel and store it into maybe store it into a capacitor or trickle charge into a battery. Okay. So, all those possibilities exist. I let you look up more detailing on LTC3105, particularly simulation with LT Spice. You could download and then try. Let us shift gears now. Okay. Let us shift gears. This is one way of harvesting power, right. Solar is so well known, popular and all that, but is that the only way by which you can actually use this? I will take another example. I will take another example of measurement of human pulse, okay, nothing but heartbeat, right. We are talking about heartbeat, and show you another way of harvesting power. So, harvesting power, difficult to use this word harvesting because I am not sure whether you are really harvesting. In this case I would say it is more power transfer of power, I would say power transfer from one device to another device, more in that sense. Okay, it is harvesting because you can say it is batteryless. I think I do not want to use this word harvesting in this case. So, it is really batteryless. So, I would like to refine my answer. Heartbeat measurement, batteryless. That is the key. See, one thing we mentioned already, that in the IoT space, if you consider gateway devices, we looked at, I did mention to you about Raspberry Pi, BeagleBone, Odroid and all that. These are one set of embedded boards. Do not forget that the mobile phone is also a very powerful, hardened, commercially available, easily deployable gateway device. So, I would say mobile phone, particularly if you talk about a smart phone. Okay. If you take the smartphone as an example, you have a number of sensors on the smartphone. Okay. Each sensor will have one novel application or the other. For example, there are what are known as inertial measurement units, IMU sensors on the smartphone. This includes accelerometer, gyroscope and of course magnetometer, right. You can also have a barometer. I will try and explain to you some nice things that you can do with this barometer. Basically measuring pressure. Okay. So you can measure pressure using this barometer. Also, if you look at communication interfaces on the smartphone, you of course have Wi-Fi, you also have Bluetooth low energy, and some phones also have in fact a large percentage of phones also have near field communication, also called NFC, right. We will not get into the detail of this NFC technology for the moment, but because it is an extension of what is the well known RFID technology, except that NFC works in the 13.56 megahertz. Okay, these chips essentially work in 13.56 megahertz as compared to RFID, which is in the sub 1 gigahertz frequency. As the name suggests, it is really near field. So you should be able to have let us say a very secure way of secure communication. It is a very secure way of communicating between two devices. Security comes for the simple reason that proximity itself is a form by which it offers you a very secure communication. It is used for several things. We will not get into that detail at the moment, but in passing it is meant for payments. Okay, one thing is people talk about secure payments. You can have e-cash loaded on your phone and you can transfer e-cash from one phone to another phone or from one NFC device to another device using this NFC. Okay, so it is also used for access, secure access. It can also be used for payments, all kinds of applications one can find. What we try to do in this NFC is NFC is well supported also by the fact that it can give you as a chip. Okay, it can give you as a chip, it can give you an output voltage. Okay, let me redraw this. I will just draw a picture of NFC chip here. Okay, it can give you an output voltage which can be 3 volts or 3.3 volts, and to which is connected the coil. Coil is interfaced. So essentially if you have a mobile phone, which also has a coil and also has the NFC chip, and there is a user, so I will simply call this the mobile phone. If you bring this mobile phone closer to this NFC system, you essentially can access the NFC memory. You can actually access the NFC memory. What it means is you can write content from the mobile phone app, let us say some app. You have an app. When I say app, I mean an Android app, or it can also be a iOS app. You could be downloading from any of the Apple websites for if it is an iPhone. So it could be any one of them. So I will just call it an app. So this app actually you can program, build a nice application with this app, and then get this phone closer to this coil. You should get nice access to this memory. You can write, you can read. So you can do read, you can do write, and you can also do interesting things, like supposing you do not want to just read and write in the NFC memory, but you want to actually write and read to, let us say, the microcontroller memory. So what would you do? The NFC would obviously support some sort of digital bus. It could either be I2C or it could be SPI. Typically it is I think it is typically a I2C or I think it is typically an SPI bus. It is an SPI, but never mind, some chips will, some components, some manufacturers will give you I2C. It is a digital bus. You can interface it to a microcontroller, typically an SoC. Let us say the SoC that we have been discussing deeply for a while now, I mean things which are popular in SoC seems to be from Nordic. The famous NRF 51822 is a SoC which has a BLE module inbuilt into the SoC, and the NRF 51822 itself is a Cortex M0, right. It is a Cortex M0 processor. Okay, it is a 32-bit processor and it is an ARM Cortex, actually ARM Cortex M0 processor. So now what you can do is, as long as the phone is paired, call it, okay, as long as it is closely paired with this coil, you should be able to do several things by writing data, reading data and so on into the NFC memory, okay. And you can also access through SPI and I2C, you can also access the microcontroller and read write into that location as well. So if there is, let us say, a flash memory location, either a flash location, flash memory or some RAM area, right, you can actually also do that. But look at what I am showing here. This chip also does something interesting, right. If you get this coil, mobile phone coil, NFC coil close to this, while you can do all of this by reading, writing and all that, I also mentioned to you that it will give you an output voltage. Now you see, you can actually use this output voltage to power the microcontroller as well, right. And essentially if you want to make a measurement using a sensor, let us say the sensor itself is connected to either the ADC port or GPIO port, depending on whether it is a digital sensor or an analog sensor. The whole chain is now up and running for you. As long as you have the mobile phone close to this coil, everything should work in practice, right. The sensor also requires power. So let us say sensor's rail also is required. So I will just show it like this. This is the sensor rail, this is VCC, this is VCC for the microcontroller, and of course ground is here. So let me redraw it so that you will see it little better. Okay, this is the microcontroller, this is the sensor which also requires VCC and all that. So look at this beautiful picture, right. Bring a phone close to a piece of equipment which does not have a battery of itself. You power this, you pair it with this coil, and somehow by magic NFC generates an output rail voltage. Connect this rail voltage to this microcontroller, and with this microcontroller power this sensor, read this sensor. Now you can do all kinds of nice things. You read the sensor value in this direction, write it into either flash or RAM, and then follow this arrow, and then either over SPI or I2C you write it back into this location and get it back to the phone. You can do it this way. You can also do it this way, that I do not want to do this path, I want to sense. So, I will take this is route A, then I will take another route B. Route B is I will get the phone. So, let us start all over. Let the get the phone closer to this equipment. This is the device that we have built. Get it closer to this. NFC will give you a rail voltage of 3.3, power the microcontroller and therefore also power the sensor. Read the sensor value route B either through ADC or GPIO, put it to the RAM or flash depending on what you want to do, and perhaps switch on this Bluetooth radio and then do a communication over a wireless. So, there are two routes. One is A route is back on NFC, route B is back on is on wireless, particularly on BLE. It is all nice. Does it really work? Do we have a product? Is this reality? That is a question, right. So, now what I will do, I will show you a demonstration, okay, and to demonstrate this Ms. Madhuri will assist me, she is right here, and we will do it together, and I will actually show you that this really works, okay. So, let us shift to the implementation the demonstration of this complete system. So, let us focus on this healthcare device, okay. This healthcare device is strapped to her middle finger, okay. So, it is strapped to her middle finger, perfect, there you are. It is strapped to her middle finger. Maybe what you should do is you should show like this to the camera, okay. Does it make sense? Okay, good. So, you can see, let us see what all she has on her finger, on her hand, on this particular the equipment that she has on in her strapped to her fingers. She has a pulse sensor which she can show you, perhaps you can see down here. This is a bought out sensor. I will give you the details as we go along. So, you can see this is the finger pulse that you want to measure. Up here she has a coil, right. This is that NFC coil I mentioned. Her controller is sitting behind, okay. You can see this is her controller here, and what she will do is she will get this phone NFC coil, okay, right like this, and she will pump energy, she will transfer energy, transfer power from this phone to this system onto a small capacitor, and then let us see what actually happens. So, let us try pairing it. For a few seconds, okay. So, now it is charging the capacitor which is part of her equipment apparatus sitting strapped to her finger, and the power which is transferred, the energy that is stored on the capacitor is used to power the microcontroller, and after that the sensor is powered, the pulse sensor is powered, and this pulse sensor is expected to be read and displayed back on the mobile device. After charging the system, the equipment that she has on her finger here, she has paired it for about 20 seconds or so, and then you can see that it has read the heart rate, nothing but the it has read it. So, basically it is a pulse sensor, it is reading the the pulse of the human. And you can see that this whole system essentially has no battery. Okay. Let me just show you the hardware. This is the hardware, and you can see that there is a small controller inside, and essentially the NRF board that I mentioned, NRF hardware that I mentioned. So, this is essentially another way of building batteryless devices. Okay. So, that is really the point. So, in this particular demonstration, what we have shown is that it has taken route B. Okay. Route B is essentially the route that it goes from the port via the Bluetooth. So, it has taken this route. So, you can try this if you wish, try to build this if you wish, and if time permits we will also try to run through the software code which will allow you to prototype this system completely. It is not that this system has no challenges, it is not that there are no challenges in this system. I will flash a few slides which will complete the story of this, and that will help you understand the overview of building a batteryless device in its completeness. So, let me now shift to a set of slides which I prepared, and here is the actual batteryless pulse meter that we showed you now. You can see that the system essentially is strapped to either the index finger or the middle finger, and you can make a measurement. So, what is the overview? It basically measures the heart rate using IR reflective method. It is an open source hardware. It uses a photodiode and ambient light sensor for pulse detection. I already mentioned to you that we use this NRF 51822 SoC for signal and data processing, and the system is powered through NFC enabled phone, and the communication is through that route B, which is essentially the Bluetooth low energy system. This is how you would attach, and this is how you would actually use it for measurement. The hardware specification, this is again from what the sensor manufacturer has mentioned. The sensor operates between 3.3 and 5 volts. The current consumption is roughly 4 milliamperes maximum. The diameter of this is also mentioned. The system specification, the overall system that we have built, operates at 3.3 volts. Current consumption is low power mode is 1.5 milliamperes. ADC sampling requires 6.5 milliamperes, and BLE transmission mode requires 13.5 milliamperes at 0 dBm transmission power. Look at that specification and look at the kind of power that you will require, right. And it is you need this kind of power, but it is doable. You can do it with the devices that we have around us. You can transfer power from one to the other and perform these kind of power guzzling, call it, because in the low power space really this is quite a power consuming electronics, right. For example, 13.5 milliamperes at 0 dBm is a big number, and so is the ADC sampling and so on. So, you could build that. It is not that the system is very stable when we were actually making a measurement. You can see that the voltage that developed across the microcontroller in the first picture that you see here on the left side here actually was quite the voltage was really unstable, and we had to do a lot of nice tweaks in order to get back a nice good waveform here, which will allow us to use and power the pulse sensor effectively. So that correction was required. So challenges was there was instability in the voltage causing unreliable sensor values. Current supply through the NFC was limited to 4 milliamperes and the system requires 3.5 milliamperes. Look at what I have written here. The power management algorithm is so important if you really want to pull this off. Usage of supercapacitor to overcome some of the current requirements. We used a supercapacitor, and it is indeed a challenging project, mini project that you can think of when you want to build batteryless devices, particularly if you want to do measurement of some critical body parameter. See, this is from, I would say it is a very nice thing from an academic perspective, but I do not think you should use this particular pulse sensor for any professional purposes. In fact, these are not FDA approved sensors. So if you are using it for some of your own personal requirement, this is a nice device that you can, it gives you the first cut, right. It is not going to give you very accurate pulse, it is not going to give you the heartbeat accurately, but maybe you know the range in which the measurement is you know the range over which such a measurement has happened. So I would say that this is purely from an academic perspective and also from a hobby perspective. Actually this sensor is from it is available in open source, and all the required hardware required software drivers for this sensor is available for Arduino. Okay, so pulsesensor.com, if you go to pulsesensor.com you can buy this at roughly $25. Buy it, if you have the Arduino kit with you, you can interface it and you will start getting heartbeat quite accurately. Apply it either to the finger, or sometimes people also apply it to the ear tip here. You can actually apply finger pulse or also ear tip you can use, and these are good places to measure the heartbeat quite effectively. So in other words, this is a nice exercise, and a lot of software hacks, a whole lot of power management algorithm which is required to ensure that the system is working successfully and you are able to read that value. So that is really an interesting way of doing things. Okay, so now I showed you solar, I showed you on power transfer, I will not call it batteryless power transfer using NFC. Okay. So let me shift back, let me go into another mode of harvesting. How can you try something, and can you do something around the humans, can you harvest something from human energy, and so on and so forth. For that, what I want to show you is harvesting from body heat. Okay, that is another interesting thing that you can think of. Okay, so let me now turn my attention to another demonstration whereby you should see whether you can actually get anything useful by exploiting the temperature differentials that exist around us. For example, if you are in an AC room, the AC is perhaps maintained at 19 to 22 depending on one's comfort level degrees Celsius, and the body temperature is typically at around 36. So, you can have roughly anywhere between 12 to 14 delta T temperature differential, and whether that differential temperature differential can be used for harvesting using devices such as which are based on the physics principle of Peltier and Seebeck effect, particularly Seebeck effect, because if you apply a temperature differential you will get a voltage output, right. So, whether we can do that, how do they look, what kind of delta T exists, can we actually pull off anything from body heat. Why do you want to do this? Well, there are many applications, particularly if you are looking at any variable space, you want to power the variables which you are using either for fitness or for normal monitoring. These systems typically are associated with a battery, right, because you want continuous monitoring. But energy harvesting has the ability to not just power those devices, which is a dream really, but has the ability to charge a rechargeable battery, which means you do not have to take it out, put it into a charging pod or whatever and then wear it back. You do not need to do that. It can be on your body and all the time you can be charging the system such that it gives you a 24/7 kind of powered, always powered device, which is which can help you to use it for many long number of years. Remember, I keep saying this, that any design that you do, if you are looking at battery based designs, any design should last for 10 years, battery should last for 10 years, right, otherwise it does not make sense. So, you should be able to charge and keep it always in a good condition, that such that the device works for 10 years without replacing any battery. For this, let me show you a demonstration of another kind of device, which essentially is called the thermoelectric generator. Okay. So, you can see this is a TEG. What I have here is a thermoelectric generator, and there is obviously, it is not very thick, there is a hot side and then there is a cold side. Okay. And I will show you. So, what I have done is I have connected it to a PCB which is right here. Okay. So, this PCB is right here, you can see that this is the PCB, and I should be able to show you what kind of voltage develops across this system. Okay. So, just follow my instruction, I will connect the hot side here to my body, okay, and I will make a measurement. So, let me put back the meter. And let us see what actually happens when we so I will connect the tag here, just use it as a support and see what actually happens at V out. You can see I am measuring 1.6 volts, it is giving me 1.6, okay, and okay, sorry. So, the input, so the output I am getting is 1.3. So, if I start heating a little bit and see what actually happens. Okay, you see I get 1.8, and what I will do is I will continue to rub so that I heat this side and let us see another measurement. You can see it has gone a little over range. Yeah, you see it is developed up to 4 volts, which is a clear indicator that if the temperature differential exists, you can actually harvest from this device. Now it is down to 3.4. Okay. I should be able to show the output. Yes, there you are. Now it is coming down. So this is another way of harvesting from body heat. Okay. What is this sensor? What are its detailing? How do we do this? Can you go back to the same standard paradigm of simulation study first, application, simulation study, and then trying to see if this system is a viable option for powering our wearable. Okay. That is the important thing that you want to study next. Let us focus on the sensor of interest. Okay. The sensor that you have seen here, the one that you see here, essentially is a thermoelectric generator. You can see it is not very thick. I repeatedly say that because you have to note this, there is a serious issue with respect to that. If there is a, and it has two sides, there is a hot side and then there is a cold side. This is the side which is the hot side, and it is written here hot, and this is the cold side. So if you maintain the differential delta T, you should be able to harvest from this thermoelectric generator, to which I have connected a piece of electronics here, and then I have shown you the output voltage across the multimeter. Let us move on to understanding thermoelectric generators straight away. Let us now focus back on the other energy harvester I mentioned to you is the thermoelectric generator, okay, and that is what we had also seen. This is another form of energy harvesting. We will get into the detail later, but you may want to actually understand how did I actually use this energy for interfacing with the electronics that I showed you on the PCB here. Essentially what I have done is I have taken the TEG, which was sort of squarish, and connected it to essentially connected it to an IC also from Linear Technologies. This is called LTC 3109. I passed through a very important block before I connected it to the LTC 3109, and I got the V out here. Okay. This is essentially something which gives you, so this is the TEG, right. So this is the TEG, and this TEG was applied to my body, right. I had connected to my body. I did not show you that, but I will show you very soon that the input which I get from the body is roughly 30 millivolts. Okay. I think it is better I shift to show you this before I move on to any other measurement. So, let me shift this back. I will connect to the input. So, let me put back this hot side to my body and I make a measurement across this, so that we know what is the input. So, it is at 20. So, let me move it. So, it measured 20. Anyway, so you see it is measuring so it measured roughly, it went up to 26. So, it is a little uncomfortable for me to make this measurement as a single person, but I will still try. So, it gives as an input of about 30 millivolts at the from the body. This is about 30 millivolts, okay, which comes from the body. And what we normally do is we pass it through a transformer. We feed this input to a transformer, which is typically 1:100, and magnify the voltage, feed it to this LTC, and then trigger the LTC to this is basically a DC-DC converter, and that in turn gives you a output. So, you could get 3.3 from this. Typically these kind of circuits with the body heat and all that, which we are actually, that is what we have been, which I showed you as demonstration, that we were actually getting 3 volts 3.3 at the output. In fact, it went even higher, right. We can even, it can go up, the setting is such that it could even go up to 5 volts. But if you want to restrict it, there is a way by which this circuit will allow you to this chip will allow you to restrict the output voltage to 3.3. This particular aspect is interesting because you will be able to put energy into a rechargeable battery. That is the key here. You should be able to put it into a rechargeable battery. Of course, you can't do this directly, right. You must have a charging circuit. I will simply call it CC, nothing but a charging circuit, because over voltage protection, under voltage protection, all that will have to be taken care. Protection will have to come in, because if you are talking about a rechargeable battery, you are looking at lithium batteries. So, lithium batteries are very sensitive to the charging characteristics have to be such that you do not overcharge it, then there is a chance of explosion and so on. So, you have to be really careful about have a good charging circuit, and you can actually use this body heat to charge the battery, and the battery in turn is powering the wearable device. All this is actually possible. Okay. So, this we will get into the detail of this, what this transformer is actually doing and all that, but let me quickly tell you that the idea here is that you could either put energy into this rechargeable battery, or you may actually make another decision that I will use this energy to always power a microcontroller only, no other part, but only to just power a microcontroller, which requires a very small amount of power. Okay. It could also be that. That is one thing that you can do. So, the tech that we are talking here is which is essentially something that has very low resistance. Okay. I will just show you that the tag resistance is something on the order of of 25, sorry, as about 2.5 ohms. Tags typically have, you should look for tags which typically have about 3 ohms or so, 3 ohms of source resistance. You will get them, you have to look out and actually purchase something that you will get in that range. So, the LTC 3109 resistance, input resistance, matches quite well with the TEG's source resistance. If you end up buying TEGs which have higher source resistance, then LTC 3109 perhaps is not a good IC. You may want to try the standard LTC 3105 or any other IC which does the MPPC part for you, right. Or you can also try TI's BQ 25504, whereby you can adjust the IC resistance, input resistance. So, that is another important point to be noted, that if you buy TEG from manufacturer A, also note that power conditioning from another manufacturer B, you have to take care that the source resistances and the IC resistance, the input resistance of the IC, both of them are matched in a manner that you will be able to extract the output voltage. Now, it is not necessary that that you are always getting only 30. So, it is possible that you will get typically 30 millivolts if you maintain a good temperature differential. You will actually get sufficiently good power output. Okay. So, the TEG that we have with us is essentially